Hello students, welcome to Sri Jayendra's Ring Zone classes. I'm your friend and mentor for coming classes with respect to physics. This is lecture number 8 of a unit electromagnetic induction. So let's begin with today's class. In today's class we are going to discuss basically two parts. First is the induced electric field and next would be the RL circuit. It's a resistance and inductor circuits. So first let's begin with the induced electric field. What is it? Let's have a look. Let's suppose understand that we have a ring having the radius r, and that ring has been placed in a magnetic field. This magnetic field could be written as the B. Now let's suppose if magnetic field in this region, if magnetic field in this region starts increasing at a rate of dB by dt, what happens? Suppose the situation is sorry, that a ring is there, ring is having a radius r, and this ring is placed in a magnetic field B. Now let's suppose this magnetic field B starts increasing at a rate of dB by dt. So if magnetic field is increasing, that means even the flux is going to be changed. That could be written as a d phi by dt. Now now this is the situation for induced electric field. I hope this is clear. So as flux is changing, as flux is changing, that means EMF is induced, and this induced EMF will give me the induced current, and this induced current shows presence of induced electric field. I hope you understand this, that we understand that as magnetic field is changing. If field is changing, that means flux is changing. If a flux is changing, we understood from the Faraday's law that EMF is induced. If EMF is induced, we can say it's a current will induce. And if current is induced, if current is flowing through the circuit, we must understand that as current is induced, so that it means we are sure that even an electric field will be induced. If this is the situation, I need to find out that what should be the value of an induced electric field. Now let's begin our research. That this work done could be written as line integral of f dot dl. I hope you understand this. Electrical force could be written as this F is equals to Q naught into electric field E. Let's put the value. It is just the Q naught into electric field E dot dl. Q naught is the constant. Let's keep it aside, and it would be an integral of, or I should say it's a line integral of E dot dl. I hope this is clear. Now what I understand is that work done, the potential V is equals to work done by charge. So from this we can have work done is equals to potential into charge. Let's call this as a 1, n, and the second unit and the second relation, it's a work done is equals to Q naught into line integral of E dot dl. This work done could be written as Q multiplied by V. This is equals to, this is, let's say, Q naught, this is equals to Q naught line integral of E dot dl. As this Q naught and Q naught is changing, as this Q naught and Q naught is changing, so I could write it's a potential, or the EMF is equals to line integral of E dot dl. Now according to the Faraday's law, according to the Faraday's law, E is equals to minus of d phi by dt. So let's write down the complete relation over here. We understood that E is equals to minus of d phi by dt, as well as I am having the relation that EMF, or put EMF, could be written as line integral of E dot dl. So if I equate this both, this is equals to line integral of E dot dl. That should be is equals to minus of d phi by dt. This E is we call as an induced electric field. This is induced electric field. I hope you understand this. And this is the relation of it. This is the relation to find out the induced electric field. Have you noted it? Have you? Did you noted it down? Are you sure? Are you sure? Now let's understood the process to find out the induced electric field. You need to do this task in two parts. Your first part would be make a line integral of E dot dl. It's a first. Second, find out the d phi by dt. And third, equate 1 and 2 with proper sign. This is the workflow to find out the induced electric field. First you need to do this. It's first you need to calculate line integral of E dot dl. Then you need to work for the d phi by dt. It's a differentiation of flux with respect to time. And third, you need to just the equate this. That's it. If you can do this, you are good enough to solve. This is for the induced electric field. I hope this is clear. Is it clear? Do you understand this completely? Have you? Have you understand this? Are you sure? Any doubts? Is there anything? Is there anything? No? Great. Let's work for the question based on this. Let's suppose understand that suppose a uniform circular region is there, and this is the centered, and this is its radius. Suppose the magnetic field in this region is given as B is equals to B naught into T. Let me rewrite this. The magnetic field in this region is B is equals to B naught into T. What you need to find it out is you need to find induced electric field. You need to find out the induced electric field at a distance r from the center for first r is less than r, and second r is greater than r. You need to do this. You need to find out this induced electric field for this region, and in this region magnetic field is given something like this, that is it is equals to B is equals to B naught T. It is changing with respect to time. So let's work for the first. It's an R less than R. So what I am supposed to do is that let's suppose that this was the region. Its radius is R, and I need to find out the location where R is less than R. Let's suppose R is there. So I need to make a certain line integral limit. This is small r, and I need to integrate this. So first it's my first task would be line integral of E dot dl. When I write this, this is equals to E multiplied by 2 pi r. I hope this is clear. This is my first task. Now second task would be to find out d phi by dt. So let's do this. So I have done up till this. It's a line integral. It's a line integral of E dot dl, which is equals to E into 2 pi r. Now second task, it's a phi. Phi would be given as it's a b dot area vector. While this area vector I need to consider that vector in which I am interested. So this is equals to b naught into t. Magnetic field is available up to this region multiplied by area, that is equals to pi r square. This is just the phi. I need to find out the d phi by dt. When I call this d phi by dt, this is d by dt of b naught into t multiplied by pi r square, and this is equals to b naught multiplied by pi into r square. I hope this is clear. This is relation number 1, this is relation number 2. So what I need to do is that this is equals to line integral of E dot dl, that should be is equals to minus of d phi by dt. When I call this line integral of E dot dl, this is simply the E multiplied by 2 pi r. This is equals to minus of b naught multiplied by pi into r square. This r and this r has been gone, this pi has been gone, so I have been left with the E is equals to minus of b naught into r divided by 2. So this is the relation where electric field, or I should say induced electric field, is directly proportional to the r. In this case it is directly proportional to the r in this case when r is less than r. I hope this is clear. Now it's a time for the second part when r is greater than r. So the situation is, this was the region, this is O, this is radius r. While I want to find out this location r, that means this location r could be the boundary of this, and this is the location r. So now again I need to do the same thing. First, it's a line integral of E dot dl. This is equals to E multiplied by 2 pi r. Second, it's a d phi by dt. For first, it's a phi, that is equals to b naught dot a. I hope this is clear. So when I write b dot a, this b is the b naught t, but the question is that does this complete region r, I'm talking about this region, does it have a magnetic field? I should say no. Magnetic field will be covered by this region only. This is the region where magnetic field is there. So flux would be there in that region only. So that's why I write it's a pi r square. I hope this is clear. Because flux is available up to this region only, I'm going to write this. So this d phi by dt could be written as, this is d by dt of b naught into t into pi r square, and that's why this could be written as, this is b naught into pi r square. This is the second task. Now let's just equate this. If I'm going to equate this, this will be E into 2 pi r. This is equals to b naught into pi r square. So this E would be equals to, this pi and pi has gone, this is equals to b naught, but that means minus of b naught into r square divided by 2 into r. This is having a relation with E inversely proportional to the r. This is having a relation with the E. So this is the induced electric field. Okay, great. Now let's plot this. That if you understand this, for the E inside, this is directly proportional to the distance, and for E outside, this is inversely proportional to the 1 by r. So if I plot this, this is induced electric field, this is with respect to the distance. So for the E inside, it would be something like this. This is directly proportional to the r, and E outside, this is inversely proportional to the 1 by r. I hope this is clear. So this is inversely proportional to the 1 by r. I hope this is clear. Is it clear? Is it clear? Are you sure? Great. Well done. So this was the induced electric field. This was the induced electric field which develops due to change in the flux, but in this case change in the flux will be due to change in magnetic field with respect to time only. In this situation magnetic field keeps on changing with respect to time, whether it could be an increasing or whether it could be a decreasing. That doesn't make a difference, but it should be changing with respect to time, and if it is so, this will produce an induced electric field. I hope this is clear. Any doubts up till now? Is there anything? Is there? No? Great. Now let's switch to the RL circuit. This is resistor inductor circuit. It's a resistor inductor circuit. So let's work for this. Initially we are going to see a growth in RL circuit. That means let's consider that here an ideal inductor is there and resistors are there. Inductor and resistor, this both are connected in series across an ideal battery having EMF E. And initially this, as you can see, that the switch S is open. Now let's suppose what I'm supposed to do is I'm going to just switch is closed at t is equals to 0. Let's have a look. It's at t is equals to 0, the switch is closed, and as the switch is closed a current starts flowing through it. And when current has already set up, current has been already set up, and it is, let's say, increasing, it is increasing at a rate of di by dt. So if I apply a KVL loop, I hope you remember KVL. Do you? Great. So if I apply a KVL loop to this, it's an A, B, C, D, A. I could write like this. It's a minus of L di by dt. For this, it's a minus of IR plus E is equals to 0. So if I solve this little, it's an E that is equals to IR plus L di by dt. So this could be written as E minus of IR is equals to L di by dt. From this it's a di by E minus IR, that would be equals to dt by L. I hope this is clear. Is it clear? Is it? Are you sure? Great. So now let's look at this. So by KVL in this loop we are having this, it's a di by E minus IR is equals to dt by L. Now let's integrate this. I am going to integrate this current from 0 to I while taking a time of 0 seconds to t seconds. So if it is, I am going to integrate this. This is ln E minus IR divided by minus of R. That should be is equals to t by L. Let's put up the value. It has been from upper limit I, lower limit 0. So this is equals to ln E minus IR minus of ln E. This is equals to minus of RT by L. And this will be ln E minus IR by E. This is equals to minus of RT by L. If I take an anti-log, yes, on both the sides it's an E minus IR by E. This is equals to E to the power minus of RT by L. This could be written as I is equals to E by R into bracket 1 minus E to the power of minus of RT by L. This E by R could be written as I naught. So this could be written as I is equals to I naught into bracket 1 minus E to the power of minus of RT by L, where I naught could be written as E by R. I hope this is clear. So this is the transient relation. When I say transient, that means it is keeps on changing with respect to time. This is the transient relation when switch has just closed and you are observing this. With after certain instant of time t. I hope this is clear. Let's discuss a certain very important time aspects, that at t is equals to 0. What was the situation? I am having this, it's an I is equals to I naught into bracket 1 minus E to the power minus of RT divided by L. This was the current. When I say it's at t is equals to 0, at t is equals to 0, even this complete will be the 1, because e to the power 0 is 1. This 1 minus 1 is 0, so at t is equals to 0, I is equals to 0. So once the switch is on, at that instant current will be 0. You can observe this from here. Now let's look at t is equals to infinite. At t is equals to infinite, this is e to the power infinite, and anything to the power infinite, but this is a negative, that's why this is would be the 0, and I have been left with the I is equals to I naught into bracket 1 minus e to the power minus of infinite, which would be this. At t is equals to infinite, this I will be given as the I naught. Now let's look at the time constant. This t is equals to L by R. So when I see this, when I observe this at t is equals to L by R, I am having this, it's a I is equals to I naught into bracket 1 minus e to the power minus 1, and this is going to be I naught into bracket 1 minus 1 by e. This is equals to 0.632 of I naught. I hope this is clear. Is it clear? Is it clear? So if you want to discuss this, in a point of view of the closed switch and open switch, you can understand this at t is equals to 0. At t is equals to 0, inductor behave as an open switch. That means at t is equals to 0, it will be open and no current will flow through it. At t is equals to infinite, inductor can behave as a closed switch, that it will be replaced by a wire. And at t is equals to L by R, only 63.2 percentage of maximum current will pass at the instant of time constant. At the instant of time constant of this LR circuit, 63.2 percentage of maximum current, while I say it's an I naught, it's an E by R, can be passed. I hope this is clear. Is it clear? Is it clear? So do you understand this? Great. Ready for the questions? Are you? Let's have a look. Suppose the question is that this is resistor and here inductor is there. Let's suppose battery is there and here switch has been pressed. Battery is of E, this resistance is R, and this inductor is L. So what they want that find current passed through the circuit at first t is equals to 0 and second t is equals to infinite. So you need to find out the current pass through circuit at t is equals to 0 and at t is equals to infinite. How will you do this? How you are supposed to do this? So when you are supposed to do this, you want to find it out at t is equals to 0. At t is equals to 0, let me use the second slide and let us discuss it. That this is the situation at t is equals to 0. That situation is, this is R, a inductor over there, but now it has behaved as an open switch. So that path is open and the battery has been connected like this. This is the situation at t is equals to 0. So when they have asked for the current can pass through this, it will reach to this, as obvious this is the open path, no current can flow through this, so it will choose this path and keeps on going. I hope this is clear. So this is I is equals to E divided by 2R. This is the situation. At t is equals to 0. Now let's discuss this thing as a t is equals to infinite. At t is equals to infinite, the situation will be something like this. This was R. At t is equals to infinite, inductor can behave as a closed switch. So I have replaced it with a wire, and this is the EMF E, and after a long time I'm going to see this. So when I see this after a long time, the situation will be battery A has been connected, current I will be passed through this, it will be moving in this. Now it has reached to this. When it has been reached to this, it is having a two path, either to go with this or either to go with this. Now look at this. This path is having a resistance R, and this is absolutely zero resistance path. R equals to 0 over here because it's a wire, and ideally we consider that wire doesn't have any resistance. So here R is equals to 0, so it is obvious that current will choose this path and nothing has been gone through this. So it is just bypassing this resistance, and when it is going to bypass this resistance, this will give me I is equals to E by R. This is the situation at t is equals to infinite. I hope this is clear. Is it clear? Is it? Do you have any doubts up till now? Do you have any doubts? No? Is it clear? Great. Look that what happens if there is a decay in the RL circuit. Let's have a look. Let's consider that on LR circuit that has been connected to an ideal battery having an EMF E, and the switch was in the position 1 for a long time. That means steady state has been achieved. That means this is connected with the 1, and let's suppose a very long amount of time it has been connected with the position 1. And in this situation, that battery is connected. When battery is connected, and as I have said, it's a steady state has been achieved. That means at the steady state current will be equals to E by R, because inductor will behave as a short circuit. That means it is going to be replaced and one wire is been placed. Now let's suppose at the instant when t is equals to 0, the switch has been disconnected from here and it is going to be connected at here as seen in this diagram. So what happened at t instant, the current has been dropped from I0 to I. Why this happens? Because initially the source of supply was the EMF. We have a battery E and that has been connected. Now that source has been shifted, and so the current will be reducing. Now how much current will be reduced and how we can identify it? Let's have a look. So by applying KVL loop to this situation, it's an A, B, C, D and A. Let's apply a KVL loop to the A, B, C, D, A. This will be equals to minus of L di by dt minus IR, that would be equals to 0. If I write it's a di by dt is equals to minus of IR by L, as negative sign is there, it represents that current is decreasing with respect to time. So if I write this, it's a di by I, that should be is equals to minus of R dt. It's a di by I, that should be is equals to minus of R dt by L, as you can see this. So if I'm going to integrate this, this will be integration of di by I starting from I0 to the I is equals to minus of R by L integration of 0 to t dt. Integrate this, integration of di by I, it's an ln. If I replace the value, it's a ln I by I0 is equals to minus of RT by L. So this could be represented as I is equals to I0 into e to the power minus of R by L into t. If this is the situation, look at this. My current was I is equals to I0 into e to the power minus of R by L into t. Yes, this was the situation that we have seen here. Now if I put t is equals to 0, on t is equals to 0, this is e to the power 0. E to the power 0, that would be 1, and when it's 1, it would be maximum current. Maximum, I mean it's an E by R. At t is equals to infinite, this is minus of e to the power minus of infinite, and when it is e to the power minus of infinite, that current would be 0. And at t is equals to L by R, it would be I is equals to I0 into e to the power minus of 1. This is equals to I0 by E, and that would be equals to 0.368, or I should say 36.8% of maximum current. It is current at time L by R. Now you might get confused that when to use which relation, because when we were in the growth of a current, when we used to have it's a growth of a current, that means the current is increasing. The maximum current was given as it's an I naught into bracket 1 minus e to the power minus of RT by L. And when it is a decay of a current, when it's a decay of a current, the situation will be I is equals to I naught into e to the power minus of R by L into T. This is the decay of a current and this is the growth of a current. I hope you understand this. Do you understand this? So the situation is you must understand that which situation does the question belongs. If they said that look at this very carefully, because this is confusing, and if we have taken and if we have opted for the wrong option, it will land us to the incorrect answer. So if they said that at t is equals to 0 switch is closed, and at t is equals to 0 switch is closed, and we say that suppose inductor and resistor starts getting current from the supply, from the supply, then it's growth of a current. Now as it's a decay of a current, as it's a decay of current in this situation, at, or I should say if this has been, if inductor behaves as a source and you use inductor as a source of energy, as a source of energy, it will be decay of current. Do you understand this? So can you identify the differentiation between these two? Yes, what makes a things different? Do you understand this completely? Have you? Great, great. So do you understand this? Great. Now let's look at the question. Suppose the situation is this is resistor R, this is inductor L, this has been connected with something like this. This is a switch, and as it has been connected, let's suppose this is E. Suppose this is E. Now the situation is that this is EMF E, this is resistance R, this is inductor L, and it has been connected with this. Now the situation is that if switch has been opened at t is equals to 0, find find I at t is equals to 0 and at t is equals to infinite. So first thing is it has been connected initially, and now we are going to open this. Now we are going to open this. When we are going to open this, when we are supposed to open this, the situation is it will be the decay of a current. And when it is the case of a decay of a current, I should write this as a I is equals to I naught into e to the power minus of R by L into T. I hope this is clear. So at t is equals to 0, at t is equals to 0, this is e to the power 0, and when it is a 0, this is current will be equals to E by R. And when the situation is at t is equals to infinite, when the situation is at t is equals to infinite, this current will be just 0. This current will be just 0. I hope you understand this. Do you understand this? Have you? Have you got this? Are you sure? Any confusion up till now? Is there anything? No? Great. Now. So the situation is that, let's look at the next question. Suppose it is something like this, that EMF is there, and let's say a resistance R1 has been connected. This is inductor, this is R2, this is capacitor, this is R3, and let's say suppose switch has been connected over this. Give me a moment. Yes, this is capacitor C. So what they want, find current at t is equals to 0 and t is equals to infinite after switch has been closed. So once they are going to close it, you need to see this. So this is the EMF E. You have been given that EMF E is given, and the resistance R1 is given, resistance R2 is given, and everything has been given. And you need to find out that what would be the situation. So basically this is a combination. Of the capacitance, that means the RC circuit, and the resistance and inductor circuit. I hope you understand this. So first thing I must understand that what happens to the capacitor and inductor and at which time. So I must know this, that at t is equals to 0, as first thing it is a growth of a current. At t is equals to 0, inductor behaves as, at t is equals to 0, inductor behaves as what kind of situation would be? What kind of? Yes, at t is equals to 0, inductor behaves as an open switch. And at the same time, capacitor behaves as the closed switch. But at the steady state, or I should say it's a t is equals to infinite, inductor behaves as a closed switch, while capacitor behaves as the open switch. I hope you got this. Do you got this? Are you sure? So let's see the situation, that first let me calculate at t is equals to 0. So now my diagram would be something like this, that this is the EMF battery, this is the R1, inductor will behave as an open switch, so it is something like this, this is R2, and now the current capacitor behaves as a closed switch, so this is R3. So as this is the EMF E, the current should start flowing through this R1 and this R3 are connected in parallel. So this is equals to I is equals to E divided by R1 R3 divided by R1 plus R3. So this is equals to E into bracket R1 plus R3 divided by R1 into R3. This is the current that is flowing at t is equals to 0. Now let's look at the t is equals to infinite. So when you look at the t is equals to infinite, the situation will be that this is the R1. At infinite, inductor will behave as a closed switch. That means inductor would be short circuited, and this will throw to the R2, and capacitor will behave as an open switch. So this is R3. I hope this is clear. This is E. So In this situation, as this path is open and this is closed, and this R1 and R2, these two resistors are connected in parallel. So when these two resistors are connected in parallel, the situation will be I is equals to E divide by R1 R2 divide by R1 plus R2. I hope this is clear. Does it clear? Does it? Do you have any confusion in this? Do you have any confusion up till now? Is there anything? Is there anything? Are you sure? Are you sure? Are you sure? Done? Great. So let's wind it up the session over here. This is all about the induced electric field and RL circuit. Please practice a lot on this kind of questions. Basically, induced electric field has a very limited amount of applications, because in that situation only the electric field, only the magnetic field can keeps on changing with respect to time. So limited amount of application is there, but RL circuits have a huge amount of applications, and it could have many questions. Please go through it. Please go for it. Practice a lot this kind of questions. This will help us. Thank you. Have a good day. Take care. Bye bye.